Hey, Algebra 2. Today we're going to talk about exponential models. So in this case, we are probably going to be doing some word problems, and we're going to read and we're going to have to figure out, does the situation represent growth, decay? Can we write an equation? And can we do some math to figure it out? There is this one model that looks like this. And the A of t represents the total amount. The small a right here represents the initial amount. The r is a rate as a decimal. And the t is going to be the time. I don't think that I stated it clearly before, but this is very similar to the other equation we saw, y equals a times b to the x. So this 1 plus r and this b determines whether you have growth or decay. I'm going to use b for simplistic purposes. But if b is greater than 1, then you have a growth function. And if b is, it's written like this, if b is between 0 and 1, then you have a decay function on your hands. So it's helpful to know which one is the A and which one is the B. And you got to know and realize that the B is always the one that's being raised to the exponent. So we have to decide if this function represents growth or decay. So everything is in the form of y equals a times b to the x. So that's my A, and the 0.95 is my B. All right, so if B equals 0.95, and 0.95 is a number that's between 0 and 1, this tells me that I have a decay function right here. It also says that you have to state the y-intercept. All right, so if you have a y-intercept, it looks something like this. We want to know where it's crossing the y-axis. If you have a y-intercept, that means that your x value is always 0. The y-intercept is at 0, comma, some number. So this says if we set x equal to 0, we can find the y-intercept. So y equals 12 times 0.95 to the 0 power. What is anything to the 0 power? It is 1. And 12 times 1 equals 12. Oh, the answer is that number. Okay. Let's do that a few more times. I wonder if that's a pattern that's going to happen. All right, so the next one. There's my A, and there's my B. If B is 2, and 2 is a number that's bigger than 1, I know that I have a growth function because 2 is bigger than 1. That's a greater than sign, by the way. Figure out the y-intercept, okay? Y equals 1/5 times 2 to the 0. Anything to the 0 power is 1, and 1/5 times 1 equals 1/5. Oh, all right, my pattern is holding. So it seems to me when it looks like this that your y-intercept is just simply going to be your A. All right, so there's my A, and there's my B, and 4/3. So you can't just look and say, oh, if it's a fraction, it's decay. That's not true, because 4/3 is a number bigger than 1. So right here, I have growth because 4/3 is greater than 1. And then I can say my y-intercept is 1/100th. There's my A, there's my B. My B determines my growth or decay. 1/5 is between 0 and 1. So I have a decay function because 1/5 is between 0 and 1. I know that my y-intercept is at 2 because that is my A. And so the first word problem, it is multiple choice. Hopefully that'll help us out. There were no jackrabbits in Australia before 1788 when 24 jackrabbits were introduced. That seems to be important. By 1920, the population had reached 10 billion. If the population had grown exponentially, this would correspond to a 16.2% increase on average in the population each year. Which function best models the population of jackrabbits? All right, so I have a times t equals a to the 1 plus r to the t. All right, so this is the formula that we're going to use that helps us with growth and decay. The 24 jackrabbits are my initial value. So that is going to be my A function that I plug in right there. I'm going to plug 24 in. And it is going to increase at a rate of 16.2%. So that is my rate. And it always is a decimal, so I'm going to move it 2 places to the left and get 0.162. The years, the 10 billion, all that, unnecessary information. So this is just going to be a general formula. We aren't going to be able to solve it, mainly because it doesn't give us a time frame here. All right, so that says 1 plus r, and my r is 0.162. I'm going to do the math right there. I get 24 times 1.162 to the t. It says it increased, and that right there is a number bigger than 1. And so that tells me that I just wrote a growth function, and it is increasing. And so that's where the number should definitely be bigger than 1. All right, so we are just playing the matching game now. And C is the one that it matches. So you just have to pick out the important information, substitute, do a little bit of math, and then just match it. Number 6, a radioactive substance decays at a rate of 18% per year. It decays. This one we're going to have to pay attention to in a minute. The initial amount is 100. Which of the following models the remaining amount of the substance after t years? All right, so I know that A is 100 because that's my initial amount. My rate is decaying, so that means that it is going down 18% a year. So I'm going to write that as negative 18%. And then when I move my decimal, I'm going to use negative 0.18. I'm starting with my general formula here. And now I'm just going to go substituting. I know A is 100. R is negative 18, so that's going to look like 1 minus 0.18 to the t-value. 1 minus 0.18 is 0.82. And so that matches B. And you got to know that that part right there determines whether it is growth or decay. And this is a decay function. Decay functions decay and go down. That's why that number needed to be less than 1. All right. Oop, no more multiple choice. Guess I gotta do it by myself. You invest $1,000 in a savings account. All right, that sounds like A. That sounds like an initial amount to me. The account pays 5% annual interest. So there's my rate. How much money will be in the account after 6 years? Oh, this one gives me a time frame. All right, so I labeled my essential parts. I'm going to write down my formula. All right, so I want to know how much I'm going to have in 6 years. So that means T is 6. The only thing that I'm doing is writing this in function notation. That 6 is just to tell everybody, hey, this is what happens in 6 years. A is 1,000. I'm going to substitute that in. So 5%. Got to remember to move it 2 spaces to the left. So that's going to be 0.05. So I have 1 plus 0.05. And then I know that T is 6, so it goes there also. 1 plus 0.05 is 1.05 to the 6th power. This from here just became pure calculator work. If you have a good calculator, it can handle this entire string. If you don't have a bad calculator, you got to know exponents come before multiplication. So at least go 1.05 to the 6th power equals times 1,000. And give or take some rounding, I got $1,340.09. We are talking money here, and money is always rounded to 2 decimal places. A cup of green tea contains 35 milligrams of caffeine. That sounds like an initial amount. The average teen can eliminate about 12.5% of the caffeine from their system per hour. Make a table to show the amount of caffeine in their system. Okay, so eliminate means that it is going down. So I have negative 12.5%. Let's move the decimal. And so I get negative 0.125. And in this case, I need to find the time at 0, 2, 4, 6, and 8 hours. Starting with my general equation. I'm going to deal with the time in a minute. So I'm going to plug in my initial amount and my rate. So for the parentheses, 1 minus 0.25 is 0.875. All right, so I have to make a table to figure out all these different times here. So t is like your